Greetings, everyone. It's Sunday, the 26th. That's why I'm wearing my Packers shirt. And so next week we actually get to start back in the lab again. I'm pretty excited. I also feel a little bit lucky. The university kind of sent orders down to all the colleges, right? The University of Wisconsin sent this order down to the College of Engineering, and then the College of Engineering said, okay, departments, you get to pick only your most important classes, only the most valuable, critical, crucial classes, and those can meet face to face. And we got picked. Right? And I think that goes to show how much support the mechanical engineering department tends to give to teaching and your experience as first year students. So I think that's pretty cool. And so I look forward to seeing you guys next week. It's just a whole lot more fun to do it this way. All right. So I don't know why this is here. Usually the way it works is as I'm riding my bike into class in the morning, I have some idea. And then I go, oh yeah, I got to put a slide in for this. And so a couple of years ago, I put this in, and I have no idea why, but it's funny. I don't know why I think it's so funny. It's like, yeah, it's a mammoth. And this is a cartoonist named Gary Larson, and the cartoon is called The Far Side. And this stuff is just hysterical, just these subtle little things like that I think are really good. So today we're going to talk about uncertainty in measurements. And this is a really, really important topic. Without doubt, as mechanical engineers, you're going to have to measure something. And it's very, very important that you know how good your measurements are. So we'll talk about that in a little bit more detail. Next slide is this slide here. Just scroll down. Why isn't it moving? There we go. Oh, the Grand Canyon. Now, this is another one. And I looked at this, I'm like, why did I put a slide of the Grand Canyon there? Hey, if you've never been to the Grand Canyon, please make an effort to get there. It is absolutely mind-boggling how big and beautiful this place is. So, why did I put a picture of the Grand Canyon in this lecture about uncertainty? And that is because, so the first time I was there, I think it was 2003, and we were getting kind of the introductory tour. You can take the short introductory tour, they give you the big overview. And so it's 2003, and then we're walking along, and there's this tour guide. It looks like a kid that just got out of college, just got out of college, and now he got a sweet job giving tours of the Grand Canyon. And he says, okay, so here's the Grand Canyon, blah, 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 and the Grand Canyon is 5 billion and 16 years old. I'm like, holy cow, 5 billion and 16 years old? That's an amazingly accurate number to get, 5 billion and 16. And I thought about this, and I don't even know what else the tour was about, because I was thinking 5 billion and 16. And so finally I said, hey, I got to ask. I mean, I consider myself kind of a scientist, and how do you know so accurately it is? He says, well, I mean, the reason I know this is the first time I came here, I was 7 years old, right? And at the time when I took the tour, it was 5 billion years old. And now I'm 23, 16 years later. So simple addition tells us that the Grand Canyon must be 5 billion and 16 years old, right? Now, hopefully you think that's kind of funny. I can't see any of you right now. Anybody think that's funny? Hopefully you think that's a little bit funny. But hopefully you also think it's ridiculous, right? Because if you give me an answer that's 5, 0, 0, 0, 0, 0, 0, 0, 016, that's implying an extraordinary degree of accuracy for a measurement that's in the billions, and you're saying you know it down to the ones, 16, is crazy. Is it 5 billion years old? Plus or minus a billion? Or maybe just plus 0 and then minus a billion? We don't know, right? And you have to indicate measurements that imply a degree of certainty. 5 billion and 16 is ridiculous. So there we go. That's... and we'll talk about that in a little bit more detail right now. So anyway, as you take a measurement, you should be aware of their uncertainty, right? How good is it? How much do you trust it? If you did it again, would it be the same? Would it be a little bit different? If someone's life depended on it, is your measurement good enough, right? Furthermore, and that's just measuring one thing, like the age of something, or the time it took, or the diameter, or the radius. But then we're going to calculate a bunch of stuff based on these initial measurements. I'm going to put on my, I think you're just recording the whole screen, but maybe I'm going to put my laser pointer on here. If we make calculations based on these measurements that are not perfect, right, we have to say, how does this uncertainty propagate? Right? All right, so You'll learn much more about this in statistics, right? Which is 324 now. And actually, we're going to start teaching this class. It won't be Stats 324. It'll be taught right here in the College of Engineering, which I think is going to be super cool. And of course, Measurements Lab. When you make measurements, it's very important to know how good they are. So you'll learn about that here. All right, so here's an example. Now, in past semesters, we would do wind turbines. This semester, we probably won't. Just due to kind of the complications of using the wind tunnels and stuff. But one of the things that we're really interested in is we're taking this wind, and these parallel lines here are a picture of wind. This is the blades on the wind turbine. And we want to get power. W usually stands for work, and then the little dot usually means a time derivative. So how much work per unit time can we do is related to a bunch of stuff, right? Many of you have seen kinetic energy before. Kinetic energy is 1/2 mv squared. This is very similar, and I'm going to see if I can get my stylus to work. So forgive me if it doesn't go well. Let's go to pen, and let's see if I can pull this off. This number right here, this is the Greek letter rho. That's a Greek letter. It's not a P. It's the Greek letter rho, and that is density, the density of the air. And then this is area. And this is velocity. Right? Many of you have seen in previous classes that kinetic energy is 1/2 mv squared. 1/2 mv squared. Well, rho is kind of like mass, right? Mass per volume. Area is the total area of the circle, right, that the wind has to pass through, the projected area of this wind turbine. And velocity is, of course, velocity. So the power, this looks like 1/2 mv squared. It's actually 1/2 rho a v cubed. Trust me, the units work out. We'll talk about that more later. So this is the power that's in the wind, right? But we're not going to get all of that, right? The power that gets transmitted from the wind into the shaft, right, is much less. This is, well, I'm just going to tell you, this is torque and speed. Torque and speed, right? Omega is angular velocity, torque. Maybe you've seen that power is torque times speed. For those of you who are really into race cars or motorcycles, you might know that. But torque times speed gives you power. And then so finally, one of the things we're interested in as mechanical engineers is the mechanical efficiency. This little letter here is the Greek letter eta. Yeah, my stylus just isn't working right today. So, well, I'm such an optimist. I'll give it a shot here. So this is torque. Okay, that didn't work very well. Not at all. And then this is speed. And yep, there goes my stylus acting up again. And this is eta, which is efficiency. All right, because I left my iPad at school, so I got to do this the old way. And efficiency is how much of the wind power do we actually extract, right? I'm getting I've got all this wind power available, and I say, well, how much did I actually get out of it? And that's what we call the mechanical efficiency of this thing. All right, you'll learn much more about efficiencies, in thermodynamics, right? A lot of people think thermodynamics is all about like hot things and temperatures and stuff like that. Really, thermodynamics is how energy changes shape, right? It starts out as kinetic energy, and then we turn it into shaft power, right? The energy goes from this kind of energy, like a flow power, to a shaft power, and what happens in between. So that's a big part of what thermodynamics is. How does it work in a wind turbine? You'll learn about that in ME 363 on fluid mechanics, which I will very biasedly say is one of the coolest classes we teach here. All right, anyway, a very important thing about wind turbines and where you build wind turbines is how much energy available. And in the wind turbine world, they call that the resource. What's our resource? How much energy is in the air that we can extract, or we can try to extract? And that depends very much on the air velocity, the wind speed, right? So here I've got a plot. I took an anemometer, and this is the thing that measures wind speed or an airspeed. And I just took a whole bunch of measurements, right, in meters per second over the course of 0.2 of a second. All right, so this is a very, very fast measurement. And here I've got all these data, right? And it's like, yeah, it looks like about 1.6 meters per second, right? But notice these are 2,500 measurements. So I must have hooked this up to an oscilloscope or something. So here's 2,500 measurements over 0.2 seconds, and I got lots of different values here, didn't I? So if I said, hey, what's the wind speed? Maybe it's not so easy to answer, right? So we have to talk about accuracy and precision, right? The measured value fluctuates, right? There's some high velocities, some low velocities. Is that because the wind is fluctuating? Is that because the instrument is fluctuating? What's up with that, right? And two, the mean is not quite right, right? Let's say that I knew, like with some magical certainty, that the wind speed is actually 1.5. But all my measurements were up here, right? So I've got precision is how tight is my grouping of measurements, and then my accuracy is how close to the actual value is it, right? So those are two important things when we make measurements, accuracy and precision. So here's an example of some data that are accurate, and data is a plural, one datum, two data, so you should say the data are very accurate, right? It appears that the center line of my data lines up perfectly with the true value, which I know to be 1.5. So we would say this is accurate, but holy cow, my measurements are all over the place. I have some measurements that are down here well below 1, and I've got some measurements that are way up here by 2, right? So a really wide range of measurements, but the mean of these data falls right on top of what I know to be the true value. So this would be an accurate measurement, but it's not very precise. Likewise, I could flip it around. I could say, wow, I've got some new, a new anemometer, some new electronics, or new amplifier, or whatever, such that I get this really tight grouping of measurements, right? Imagine if you were, practicing with a bow and arrow, and every arrow hit like the arrow before it, right? But they were all off, right? So this is very, very precise, but since it's off a little bit here, it's not very accurate, right? Accurate but not precise, precise but not accurate. Many of you have seen this in a science class, so this is review. If you haven't, there you go. All right, accuracy is whenever you have an instrument, thermometer, anemometer, accelerometer, something that measures something else, you always want to know how accurate it is. And that's like in the fine print, I was like, oh, sweet, I got a thermometer, right? I'll get this one because it's cheaper, or this one because it's smaller. Well, that usually comes at a cost, and the accuracy is almost always published, at least for good stuff. The accuracy is published by the manufacturer. They have to say how accurately do you know the measurement? How confidently do you know that temperature? So there you go. Okay, now precision, right? How do we quantify the precision, right? We have to put numbers on it somehow, right? And the one way is to do it is to eyeball it, right? Here is velocity, and here's a little delta velocity. What's our little change in velocity, or what's the uncertainty in our velocity measurement? We could just eyeball it and say, well, yeah, that's bad. Yeah, it could be a little higher, could be a little lower, so I'm going to say it's roughly that, right? You just look at it and eyeball it. And in a lot of certain instances, a lot of circumstances, that's fine, right? I know my uncertainty here is on the order of 0.2 meters per second, 0.1 meters per second, something like that, right? It's not, I don't know this to 0.00016 meters per second. Likewise, I know it better than plus or minus 2, right? It's roughly plus or minus 0.1 or 0.2. So eyeballing it, totally okay in many situations. A little better way to do this is to look at the distribution, right? And if I took all these measurements here and I binned them, I said, how many times did I get a 1.65, right? And I put those in a box. I'm like, okay, yeah, I got a lot of them. How many times did I get a 1.60? All right, well, I got a bunch of those, a bunch of 1.68s. So I get a whole bunch in the middle, right, that are right around 1.61 or 1.62. I get some, that are a little bit more, a little bit less than that. And then there's a few that are way out there, right? These are, the tail ends of it here, okay? And notice it makes this very interesting shape here that looks like a hump or a bell or something like that. Sure enough, this is a bell curve or a normal probability distribution. Right, that's the word normal. I'm not sure where that comes from, but it's called normal. We can fit that. There's a really slick little equation that makes this curve. And we discover that many, many things in nature are distributed normally, right? The levels of chemicals in your blood, the levels of sunlight on a given, the hours of sunlight on a given day, or the masses, or the dimensions of parts when they come out of the factory, right, are oftentimes normally distributed. There are some variations on the same theme, but many, many things, the heights of students in a classroom, the weights of students in a classroom, whatever, right? Many natural things are defined by this normal probability function. So, where did we get this? The first person to really define what this is this guy. His name is Carl Friedrich Gauss. Now, I think Carl Friedrich Gauss is cool enough that my son's middle name is Carl. And so this is before the days of the euro. This is the 10 Deutschmark note, right? So it's like the equivalent of a German $10 bill. And if you look closely here, let's look closely there. This is what the Germans choose to put on their money, right? They said, wow, we have this really famous German mathematician. There's a lot of them, but this is probably the most famous. Really smart guy. I'm not sure what this hat is. He looks like he's about to go to bed or something. Anyway, so he discovered that he can use this equation, 1 over the standard deviation times the square root of 2 pi raised to the e, or times e to the power of some other stuff here, and it makes this bell curve, right? Really an earth-shattering thing. And the Germans thought it was so important that they put it on their 10 Deutschmark note. Well, compare that to the United States, the $1 bill, right? And what do we put on our $1 bill? Here's a pyramid with the top is like floating and glowing, and there's an eyeball in the top of the pyramid, right? And surprise, surprise, right? The Germans make Porsches and BMWs, and we don't, right? Now, to be fair, German cars have come a long way in the last 20 years. I mean, such that American cars are probably now as reliable as German cars, maybe even more so. And say companies like Volkswagen have had their problems. But anyway, I thought it's interesting that the Germans put math formulas on their money and we put floating eyeballs. So anyway, if we fit this, and maybe you guys have seen this in a statistics class, if we fit this curve, right, to these data, and we tweak these, like tweak these values of sigma and mu and stuff like that so that the curve fits the data nicely, then we can say, all right, I'm 90% sure, right, that my that all my measurements, so if I make these measurements, and this is 1.62, right, I can say I'm 90% sure that the actual value is somewhere in between here, right, plus or minus 1.65 of these standard deviations, right, and I can calculate the standard deviation. Again, you'll learn more about this in statistics. But if I want to be more sure, well, then I have to go way out to here and way out to here. Right? If I want to really be 95% sure, I've got to say, well, it's somewhere between 1.54 and 1.72, right? So you're saying, well, that's a pretty big window. But yeah, if you want me to be 95% sure, I have to make my target a little bit bigger. And if you want to be 99% sure, you've got to go all the way to 2.58. So now we're way out here. So if I want to be 99% sure that the wind speed is in fact 1.62, I've got to say, well, if you need that kind of confidence, it's somewhere between 1.46 and 1.76, right? So the window all of a sudden gets really, really big the more confident you need to be, right? And that's the beauty of making measurements. People who aren't scientists, people who aren't mathematicians, this is important enough that I'm going to go down here. How do I get down here? Boy, this is really causing me trouble. Oh, I got to go back to my pointer. Anyway, whatever. People who aren't, mathematicians, engineers, scientists, they want to be sure. Well, what is it? What's the value? Is the global warming caused by people or not? Well, no good scientist will ever say absolutely yes. They'll say, I'm 90% sure that it is. I'm 95% sure that it is. I'm 99% sure that it is. Or maybe I'm only 30% sure that it is, right? A good scientist never talks about absolutes. They always talk about confidence intervals. What's our confidence in the measurement? What's our confidence in the prediction? Right? So really, really important stuff. So how do we actually do this? Right? Again, say we're trying to find the power. Actually, you know what? I'm going to stop here. I'm going to make the next one a new video. So go back to the pointer here. And we're going to pause this. And now I need to stop the recording. Whoops. How do I stop my recording?